Again, so let's think like historically. So what did people have at this point? So they presented, like we did, the foundation for the world of electricity, right? So that's Gauss's law, right? And then if you know how to find electric field and if you know how to find electric force, you have a foundation in the world of electricity. You are the king of that world, right? Then if you know how to find magnetic field and if you know how to apply magnetic force, you are the king of the world of magnetism. So pretty much at this point, people felt, again, a few hundred years ago, felt like, okay, work is done. So we know everything about this world. We know we have foundation of that world. So now we should be able to describe any phenomena that we could observe. And at that moment, when people felt like relaxed, happy that the job is done, all right, Faraday came and he said, you know, guys, I found something. I found some phenomena which couldn't be explained by any of your fundamental equations. These geniuses, right? So they think too deep. They, I don't know, think maybe too much, right? And they usually find something, right? And as a result, all these sand castles which were built before them, they just crash all these sand castles. And that's what Faraday did. He was really a brilliant experimentalist, right? Probably I would consider like a genius, right? So he did really lots of things, successful things, right? So he came with some phenomena and he ruined all these well-established sand castles. Damn these geniuses, right? He was lucky he was not born like a few hundred years before that. Otherwise, he would end up like Giordano Bruno, right? You know the fate, his story, right? Right. Too smart for society. All right. So, what did he observe? And why did he ruin these sand castles? He observed this. So he grabbed a loop, or for the stronger effect, you can take a solenoid, basically lots of loops, right? Then he took a permanent magnet, right? And he started moving this permanent magnet into this loop, into the solenoid. And he connected the ends of the solenoid to a galvanometer, basically a device which allows us to see the presence of the current in the loop, okay, in the circuit, right? And he observed this. So whenever he moved the magnet in, galvanometer's needle was deflected into one direction, to one side, basically showing that, let's say, current was in clockwise direction, for example. I'm just making it up. Then he observed when he stopped moving this magnet, current disappeared. So needle on the galvanometer was 0. Usually during the normal classes at school, I usually go to stockroom and I show this demonstration. I would usually bring the galvanometer, big solenoid and permanent magnet. But here at home, I don't have that, right? But anyway, so then what else he observed? When he pulled this magnet out, needle was deflected in the opposite direction, telling us that current in this loop was in counterclockwise direction. So in clockwise, if you don't move, there is no current. When you pull this out, current is in the counterclockwise direction, right? So basically, by doing this, he started producing current. And this phenomena wouldn't be explained by any of the equations which we introduced so far. So what can be done in the cases like this? It happens almost every time in the, especially the big, a few hundred years ago. So what can be done in this case? Basically, it means that that our foundation is not complete. So it means that either you have to adjust you have to adjust sort of current equations, okay, equations which they had back then, or they have to introduce a new equation, a new law. All right. And it happens like all the time. It's like, for example, like in hydrodynamics, right? So when people try to explain, phenomena in liquid, so, and there are some fundamental equations. So how did they write these fundamental equations? they see, okay, something is happening over there in the liquid, right? So in order to explain that, we need to add, for example, this term into the equation. Okay, so let's add it. Okay, it doesn't explain exactly what we observed. Now let's adjust it slightly. Okay, let's massage these factors or terms, right? Okay, so now it explains it. Okay, great. So then somebody noticed there's something else. Then they started thinking, what can be done? So we have to adjust somehow our equation. So they will add an additional term, right, and fudge that somehow in order to explain what they observe. So, and they keep doing this until they can explain everything that they observe around themselves. So, and now the same. So now Faraday found some observation which couldn't be explained. So now there are two ways: either adjust the given equations which they had, or present a new one. So they presented a new equation, fundamental equation. And that's why it is called law. It's a true law. And of course, since he observed this phenomena first, so it has his name, Faraday's law. Again, it's a fundamental equation. Basically, we treat it as an axiom, right? It cannot be derived. Again, it was written based on observation, so it can be applied at any point of the universe, at any moment of time, by anyone, no restrictions whatsoever, right? So, and this law, it's the third law, third equation in the set of Maxwell's equations. So you see, now we realize that our foundation was not complete. So Faraday's law must be added. So now we will have three equations from the set of a set of Maxwell's equations: Gauss's law, Ampere's law, and now Faraday's law. Three. We will have to add at some point one more equation, but for now, three equations. Right? Okay. So enough of the introduction, and now sort of what was the sort of logic? Which logic can we produce to sort of present the Faraday's law? It will take quite some time to present finally the Faraday's law. Look, we observed just in the recent past, then whenever you have a wire with a current, whenever you have a current, of course, there is a magnetic field around that wire, right? And we know how to find this magnetic field. But then, of course, you can ask, if you are too curious, you can ask yourself, like a curious George, right? Of course, you can ask yourself a question. Is it possible a reverse process? Inverted process? Is it possible somehow to produce electric current from the magnetic field? Why not, right? So that's how research is done. They raise some questions and then they try to answer them. So is it possible to create an electric current from the magnetic field? And of course, what we just observed, that yes, it is possible. And of course, this observation basically changed the whole world. Right? This discovery changed the world. And of course, you know why I'm talking, why I'm saying this. Because basically now it allows us to power the whole industry, right? And this is the picture of generators, right? And of course now people of Lowell, okay, where the university is, of course, can blame Faraday's for the decline of this city. Because what, back in the end of 19th century, the end of 18th century and then 19th century, right? So the Lowell was blooming, right? Because of what? Because all these textiles mills needed these Pawtucket Falls, right? To drive these machines, textile machines, right? And the Lowell was happy, right? But then when electric current production was discovered, right? So and then river was no longer needed, so people could run these machines, right? Textile machines using electricity. So there was no need in the river. Plus, back then, unions started getting stronger and stronger, demanding more from industrialists, right? More salary, more benefits, and so on and so forth, right? So the industrialists kind of thought a little bit, right, and decided, you know what, we're moving out from here. We no longer need your river, right, and your city. We'll just move to the south, right? For example, to Georgia, closer to the cotton plantations and so on. Plus, there are no unions, right? So we can profit there more. So as a result, Lowell started going, and Lawrence together, right, and some other cities, they started going down, right, really down. Right. So we can blame Faraday for that. Right. Of course, I'm blabbing, right? But anyway, you got the point, right? And also, can you imagine? So now people try to patent almost everything, right? So they just bend something in the opposite direction. So let's patent this, let's patent that, right? So can you imagine if Faraday patented this discovery? By this time, he would own the whole world. I don't know, Bill Gates or Bezos would be just poor people relative to him because production of electricity is everywhere, right? So this is really remarkable, right? So what he, of course, discovered. Okay, so now let's again see what I just told you. I told you what he observed, right? So by moving magnet in and out, right? And what is important, right? I want to emphasize. So when you don't move a magnet, current in the solenoid is not produced. We need to clearly realize that. So you must move it in order to produce current. So clockwise, counterclockwise, clockwise, counterclockwise. Right now I'm doing what? I'm basically a generator, right? AC current generator, expensive current generator, right? So we need to clearly realize that in order to describe that, some quantity which we don't know right now which quantity, but that something must change in time in the law, right, which we're going to present. And of course, why we're trying to connect EMF with changing something? Because if there is a current in the loop, there must be an EMF, potential difference, produced somehow mysteriously in the loop. Because current, it's a consequence of the presence of the potential difference, EMF. So if there is an EMF, there is a current, right? So we can observe that. So in order to write this law, Faraday's law, EMF must be equal to the rate of change of something, because as I showed you, so you must move the magnet in order to produce EMF. If you don't use the magnet, if you don't change its position in time, as a result, something changes in time. Only then current and EMF is produced. So right now we're not ready actually to present Faraday's law. We need to discuss that something. And you remember something like this we experienced when we tried to introduce, you know what, let me adjust slightly something. When we tried to introduce Gauss's law, right? You remember we had to pass when we compared with Yankee swap, right? And then I told you guys, you know what? We're not ready to present Gauss's law, and we digressed and we spent the whole class introducing electric flux, because electric flux was the key player in the Gauss's law. Now we're in a similar situation. So we realize that we need to introduce something in order to introduce Faraday's law. Now let's discuss that something. And that something is, if back then we digress to introduce electric flux, now we have to digress to introduce, guess what? Magnetic flux. That something is the magnetic flux. But now, of course, we're going to move much faster, because the difference between these two fluxes are only just change the name electric field with the magnetic field, and the rest is exactly the same. Exactly the same idea. What is a magnetic flux? It's a number of magnetic field lines crossing a surface, right? So electric flux, it was number of electric field lines crossing the surface. You remember we spent quite some time playing with that flux, and now we will move much faster through this, because the idea are extremely similar, extremely similar. Right, so let's start with the simplest possible situation. Again, every time in order to have a flux, magnetic flux, you must have magnetic field and some surface. And then magnetic flux, it's a number of magnetic field lines crossing that surface. Simplest possible situation. Uniform magnetic field, you see, density of lines the same, and flat surface. Again, we need to introduce our area vector, that strange, weird vector. And at this point, since this surface is open, you have a freedom to choose a direction of the area vector. You can point it that way, or you can point it in the opposite direction. It's up to you. At this point, you have freedom, right? And so in exactly the same way, we can introduce for this situation, magnetic flux as a dot product, scalar product between the magnetic field and the area vector. Electric flux we introduce as E dot A, but now it's a B dot A. And of course, if you write it explicitly, it will be B times A, absolute value of B, absolute value of A, and times cosine of the correct angle between these two vectors. And of course, this is the correct angle because tails of both vectors are at the same point. So that is the correct angle. Right? So that's magnetic flux for the simplest possible situation. But in the case if you have a magnetic field which is not uniform, surface which is not flat, and like we discussed in the case of electric flux, we can write a very similar formula. It's a surface integral, of course. Surface integral of B dot dA. So you take your surface, you slice it into small patches, right? Take a small patch, right? So write the flux for that patch. It will be B dot dA, right? And then integrate over the whole surface, like we discussed a few weeks ago already, right? So now we introduce the magnetic flux, number of magnetic field lines crossing a surface. We introduce new quantity, and then what's next question should be? All the time I ask you. Should we introduce a new quantity? Special, wait, should we introduce the special unit for this quantity? When we introduced the electric flux, you remember, we didn't introduce the special unit. So we just, whatever we saw, newtons divided by coulombs times meters to the power of 2. So that was our unit, right? But now magnetic flux. And magnetic flux is used in the Faraday's law. We will see in a few minutes, right? And Faraday's law describes production of electricity, right? And of course, production of electricity is almost everywhere. It is used by technicians. This equation is used by technicians, engineers, researchers, tons of people, right? Use this magnetic flux. So it makes sense to simplify their life at least a little bit. And instead of pronouncing every time flux, I don't know, 5 Tesla times meters to the power of 2, I don't know, it makes sense to introduce a special unit to make their life a little bit easier. Weber. Right. So 1 Weber, it's a 1 Tesla times meters to the power of 2 square meters. Right. Although if you write units Tesla times meters to the power of 2, it's not wrong, it's correct, right? But if you use it a lot, of course, it's much easier to pronounce and write Weber, right? And symbol WB. Okay, so now let's play a little bit, let's look at a couple of examples. Magnetic flux. What about time? Okay. A minute left. So let's start with this question. So a couple of examples. Uniform magnetic field. You see dots. It means magnetic field is out of the page. Then we have a square loop, right? And this square loop is dragged that way. Okay, assume that this magnetic field doesn't end at this line. It just, this magnetic field goes all the way to that infinity. So, and this loop is dragged that way with velocity v. What can you say about the magnetic flux? So we have the surface, we have magnetic field. Of course, we can introduce magnetic flux, number of magnetic field lines crossing this loop. So can you tell, is the magnetic flux through this loop changing or not? Right? Two options, yes and no. Okay, very quickly, right? So you answer, and it's a test 2. Okay. And this question we're going to answer many times when we will start applying Faraday's law, because magnetic flux is a crucial part of the Faraday's law. So every time we will be analyzing what happens to the flux, what happens to the flux, is it changing or not, is it changing or not, and how is it changing, right? So that's why I started with this. Seems to be like simple question, because we will be doing it a lot. It's a simplest possible case. Uniform field, flat surface. So we can use the formula. Slides forward, which we just discussed. B dot A. So, and if you write it explicitly, it's a BA times cosine of angle between them. So basically, in order to come up with the conclusion what happens to the flux, we need to analyze these three parameters. Again, every time three. B, A, and the angle, theta. So let's do it one by one. Magnetic field. What happens to the magnetic field through this loop? Nothing. It stays constant. So B is constant. Then area of the loop also stays constant. We don't distort the shape of the loop. So A is constant. And what about the angle? Angle, okay, it will be also constant, but you can make it 0 or 180 degrees. If your area vector is out of the screen, no, yeah, out of the screen, like in the direction of the magnetic field. If your area vector is out, then of course the angle will be 0, but anyway constant. But if you pick area vector into the screen, opposite direction to the magnetic field, in that case angle will be 180 degrees, but anyway constant. So theta is also constant. So if all three parameters are constant, of course flux is constant. So in this case flux flux is not changing. All right. So from now on, I'm going to use these three parameters all the time when we start discussing Faraday's law, right? In order to find out what happens to the flux. Every time I will be analyzing B, A, theta. Now the next question, very similar. Basically, you see the same magnetic field, the same direction, the same loop, but now this loop is being rotated. So you see two sort of like rods connected to both sides, so we can spin this loop around those rods. So what about the magnetic flux now? Is it changing or not? And now you see how it should be analyzed, right? Okay, give it a try. So now it's conceptual test 3. Okay, I see you started answering. Awesome. Again, three parameters. We have the simplest possible situation. We have a uniform magnetic field, flat loop. All right, so we can apply again B dot A, BA cosine theta. Again, three parameters, BA theta. Let's analyze one at a time. B through the loop, constant. We don't change the magnetic field, right? So B is constant. Then area of the loop. Again, we don't change the shape, we don't change the area of the loop. So area is also constant. But what about angle? So again, it's an angle between what? Area vector and the magnetic field. Magnetic field is out of the screen towards you, right? So now let me start with area vector. Okay, let's say this is my area vector. And first it is aligned along the magnetic field lines. So right now the angle is 0 because magnetic field that way, area vector that way. Let's say this is my beginning. And now I start spinning it. So now the angle is 30 degrees, 60, 90, 120, 180, 230, 270, and so on, 360, then the 420, and so on. So as you keep spinning, the angle keeps increasing, 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 and increasing. So in this case, angle is changing, right? Angle between B and A, and as a result, magnetic flux is also changing, right? So it's not constant. So the flux is not constant. So in this case, yes. So that's what we're going to do pretty much today several times, and then next class, tomorrow is Friday, yeah. So and then tomorrow most likely we'll spend the whole class doing something like this. And now Faraday's law. As I told you already several times, Faraday's law is one of the fundamental laws in physics, right? Again, it was written based on observation, so it cannot be derived. We just need to present it and start using it, right? And usually, I already sort of described how these laws are usually written, right? I usually call it like a Frankenstein's method, right? So you see something, right, and you start putting together, right? So the head, right? So the arm, right? So the leg. So in order to represent what you see in the nature, right? So basically, it's called fudging, right? But axioms are like that. So here's the Faraday's law. EMF right? Basically, electric potential, potential difference somehow mysteriously produced in the loop. Again, so you have a loop, conducting loop, which is exposed to some magnetic field, external magnetic field, right? So since there is a loop, there is a magnetic field, of course, there must be a magnetic flux. And that's what we have in this law, right? Phi sub B. It's a magnetic flux. B stands for the magnetic field B, because we use the symbol B to denote magnetic field. So, so there is a magnetic flux. And if this magnetic flux changes in time, if derivative d phi over dB is not zero, then there's a somehow EMF potential difference is mysteriously produced in this loop. Oh, you can think like a bunch of very, very small batteries is uniformly distributed over this loop, right? So if you start at this point, let's say it has some electric potential, and when you move around, get to the same point, so electric potential now will be different, right? And it is equal to EMF. And so it is equals to it is equal to the negative rate of change of the magnetic flux. So flux must change in order to produce EMF. If flux is constant, nothing is going to happen in the loop. So these are in words, right? So Faraday's law. So now, of course, if you write explicitly the magnetic flux, of course, it's a you can write it like this: EMF equals to minus d over dt, b times a times cosine of angle. Again, so that's why we will have to. We already analyzed these three parameters, b, a, theta, and now we will continue analyzing these three parameters every time. And again, every time it's like three parameters here, three quantities over there, right? So now again, three. Magic number. All right. Okay, so it means that we can produce EMF, and of course, as a result, consequence, there will be current. If there is an EMF potential difference in the loop, of course, there will be current. So we can produce EMF and also, as a result, current by, for example, like in this case, if you have a loop and move permanent magnet closer and closer and closer, so in this case, which parameter changes? Most of the time, mostly B, magnetic field. Since you move magnet closer and closer, of course, magnetic field through this loop is getting stronger and stronger. Of course, angle will be also slightly changing, right? Or maybe not so slightly, but let's assume that angle is constant, right, for simplicity. So in this case, we can say that mainly magnetic field changes, the value of the magnetic field changes. As a result, EMF will be produced in this loop, and current will flow, induced current. This current is called an induced current. Then second situation, what if we have uniform magnetic field and there's a loop like this, and we spin this loop around this axis, right, around this axis of rotation. So now which parameter changes and gives us non-zero EMF and of course current? In this case, angle changes, right? Angle is changing, we can say. Yeah, angle is changing. B is constant, area of the loop is constant, right? So, but angle is changing, so EMF in this loop will be produced and we can use that current. Or the last situation, area can change. For example, let's say we have uniform magnetic field, and let's say first the circular loop had this radius, larger, and let's say you change something. Maybe you change temperature significantly, right? And this loop is shrunk, right? So area has changed over time. So flux changed over time, and as a result, in this loop, there will be current flowing clockwise or counterclockwise. We will see about the direction soon. Right? Okay, so every time B, A, theta, we'll have to analyze three parameters in order to figure out are we going to have EMF and induced current or not. So now, Lenz's rule. Okay, so again, here is the Faraday's law, right? And you see that minus in front. It sits there peacefully, innocently, but it's very important. Basically, that minus is responsible for a direction of current and direction of EMF. It just tells us if current is current going to flow in a clockwise direction or counterclockwise direction, right? That minus is responsible for the direction. And actually, using that minus to get a direction in this formula, it's not the most convenient, right? And not the easiest, right? So if something is not very convenient, people are smart. They will try to introduce some rule, right? Maybe mnemonic rule or something similar, to replace that unpleasant procedure with something which is more pleasant, right? It's just normal, natural, right? We're all like that. So I guess Lance was not happy with that minus, so he introduced the Lance rule. And again, everywhere books they usually write Lance law, but now you got my opinion, right? Law is something fundamental, right? This is a great, nice mnemonic rule, but which allows us to find direction of current and direction of EMF. But I prefer to save word law for something fundamental, important, right? Okay, so now if we're going to use Lenz's rule, then the process of finding EMF using Faraday's law can be divided into two steps, and we're going to do it all the time. So the first step, of course, you can change those steps, right? Order those steps you can change, right? So, for example, first you can find, for example, absolute value of EMF. Just drop that minus. You see the sign of absolute value, just absolute value of d phi over dt. And then second step, instead of dealing with that minus, you can just apply Lenz's rule. Right? And we're going to follow these steps. But again, as I said, sometimes you can find, you can apply Lenz's rule first, and then you can find EMF. It doesn't matter which step you make first. The fun part, this Lenz's rule, it's not completely trivial, and that fact makes it, I don't know, more appealing, at least for me. But I find it elegant, nice. So this is the statement of the Lenz's rule from the book. Whenever I read this, it makes me sad, right? It's sort of like a reading, I don't know, conditions when you take something from the bank, right? So it's written in such a way that to confuse you, to bore you, right? So this is the way this law is written. Okay, rule is written, and that's why I put that cat, right? So let me present this rule in my way. And I present it in three steps, basically three levels, right? So first kind of very shallow level, then a little bit deeper, and then we'll eventually present this rule. So first, the shallowest level, physical-philosophical level, right, of an introduction. Okay, guys, most of you experienced it, and you know that any system in the universe, doesn't like changes. I experience, me as a system, right, one of the systems in the universe, I experience it every morning. Like I experienced that 2 hours ago, trying to wake myself up, right, and get up to run this class, right? Because my system, it wanted to sleep, right, and I had to use, I don't know 3-4 alarms, right, to get me up, right? And I'm sure that you experienced something like this. Yeah, because my system want to continue sleeping, right, instead of preparing the class, right? Or if we look in physics, right, you remember Newton's first law. What is effectively that, right? So if you have a point mass, right, and it is if no forces acting or net force acting on the system is 0, then this object is going to travel in the same direction with the same speed forever and ever. By itself, the system, this object, is not going to change the state of the motion, direction, and the speed, right? So it is going to keep the same speed and the same direction all the time. Because by itself, no, it doesn't like changes, right? So in order to change, for example, the speed, you need, or maybe direction, you need to apply the force, basically external influence, right? Because by itself, the system, no, I don't want to change. I don't want to change anything, right? I want to flow with the current, right? So another example where a system doesn't like changes. So what about our system? We have a loop exposed to the external magnetic field. So what our loop doesn't like? Doesn't like, I mean, changes in what? This loop. Yeah, what our loop doesn't like. Right. Which changes our loop doesn't like? Our loop doesn't like changes in this magnetic flux. This loop wants to keep magnetic flux as constant as possible. If the flux through the loop is constant, then the loop will be completely happy. It will sleep, right? And without producing any EMF or current, right? Because if flux is constant, it means that rate of change of the flux is 0 and nothing is going to happen in the loop. It will just sleep peacefully. But once you start changing the flux through the loop will wake up immediately. Oh my God, you're changing it through me. I don't like that, right? And it will start responding. It will start doing something. It will start reacting on your actions. And of course, there are two situations. This flux can grow through the loop, or the flux can die. Right? So let's discuss both of the situations. So we have a loop exposed to the external magnetic field. Of course, this external magnetic field creates the magnetic flux. And in the first situation, let's assume that this magnetic flux is growing through the flux. Of course, the loop doesn't like it, right? So damn it, you're changing flux through me. And of course, it is start doing something. And what does it do? It will start suppressing that growing flux, trying to make it as constant as possible, right? Of course, it will never be able to suppress it completely, no, but it will be able to reduce the growth level, right? So it will try to do everything possible to reduce the rate of growth. It's basically, in this case, loop behaves like a rebel. It rebels to your action. Flux is trying to increase and the loop is trying to suppress it like a rebel. And what's the most famous rebel in the 20th century? For me, it's in my mind, it's probably like that Che Guevara, right? You remember that famous character. Where did he live? I think he lived in Nicaragua and then in Cuba, right? And the students in American universities in 70s liked him a lot, right? You remember those T-shirts with his face, right, on the T-shirt, right? Right, so it behaves like Che Guevara. It rebels, right, trying to suppress the flux. How it rebels, we will see in a second, right? But for now, we just need to realize if flux is growing, the system behaves like Che Guevara. It rebels, right, trying to suppress. Okay, so now the second situation. What if that magnetic flux produced by this external magnetic field is dying in time? Again, the loop is not going to like it, right? Again, the loop will wake up. Damn it, you're changing again the flux through me. I don't like that. And of course, now it will start. It starts responding, but the response will be different. Now it sees the flux is dying. So what should be what will be the response of the loop? It will start supporting, because you remember it wants to keep flux as constant as possible. It doesn't like changes. So in this case, the system, the loop, becomes supportive. It will support dying flux. It's sort of like, I know, I compare it with like Florence Nightingale in the 19th century during that Crimean War, right? Where she was helping soldiers. Anyway, that flux will die sooner or later, right? But this but let me hold you for a couple of more minutes. It will die sooner or later, right? But the loop will help to live it longer. It's sort of like Florence Nightingale. Oh, you poor thing, you're dying, right? Let me help you. You will suffer longer, right? Because I'm joking, right? But anyway, so you see two completely different responses. If flux is increasing, the system tries to suppress it. If flux is dying, system tries to support it, becomes supportive. Che Guevara, Nightingale, Florence Nightingale, right? And now let me introduce the three, sort of now the second level, the three major players. All right, three major players in this game. And those are, okay, electromagnetic players, right? So, of course, there is a loop. This is the major player, but I want to talk about electromagnetic players. So first, an external magnetic field, which creates all this mass, right? So external magnetic field. Then there will be a response of the loop, and the response of the loop will be in the producing of the induced current. So the loop will start driving current through itself. You know what? It sounds so strange, so bizarre even, right? So you see, the loop doesn't like changes. And if you start changing it, right, so of course it will start reacting, started doing something. You're changing flux through me. I'm going to, for example, rebel, right? And what's the response? The loop start driving current through itself. It's sort of like an electrocuting itself. It's so masochistic approach, right, of the system, right? So, so I don't like that you're changing flux through me, or so let me drive the current through its. The loop starts driving current through itself, right? Very interesting approach. But anyways, okay. So the second layer is this induced current, and now it's time to introduce the last player. So whenever there is a current, of course, there will be immediately a magnetic field produced, additional magnetic field, secondary. And that magnetic field we're going to call the induced magnetic field. So within the loop, okay, around the loop, there will be also induced magnetic field. So now we have three players, two magnetic fields. The first, the original, the external magnetic field, which produces all this mass. I usually use red marker. Then there will be secondary induced magnetic field, which is produced by the second player, which is the current, induced current in the loop, right? And I like this idea, the loop is electrocuting itself in the response of your actions. Yeah, it's very funny. And now let's finally introduce the whole rule, right? And of course, two situations. First, flux is growing. Second, flux is dying. So let's start with the growing case. So again, loop, conducting loop, exposed to some external magnetic field, initial situation. And if magnetic flux produced by this field is growing, the loop doesn't like that. It wants to keep flux as constant as possible. So what's the response of the loop? The response of the loop in this case, it starts driving a current, induced current, in such a direction. You know what? It's so funny, a response of the loop. Let me digress for a second. Right? It's really a funny response of the loop. It doesn't like something, the fact that flux is growing. And what it does? It starts driving current, electric current through itself. It's sort of like a self-electrocuting, right? So I don't like that you do something, so okay, let me drive current through myself, right? It's very weird response, right? Sort of like creating self-electrical chair your own, right? I don't like what you do, okay, let me drive current through myself.
So
But that's
why?
what the loop but that's what loop does, right? I'm just blabbing. Okay, anyway, so the current starts flowing through the loop, and of course, in such a direction, so that the induced magnetic field, you remember the third player, induced magnetic field, is in the opposite direction to the direction of the external magnetic field. You see here cup this way, here cup that way. So it starts driving current. Right now, we don't know the direction of the current, but we know it starts driving current in such a direction so that the induced magnetic field is in the opposite direction to the external magnetic field. Why opposite? Because the loop tries to suppress the growing flux. And if we have this situation, then what happens? This flux can be, for example, positive, right? And then the flux produced by the induced magnetic field will be negative because directions are different, right? You can pick area vector this way, so this flux will be positive, but flux produced by this blue marker will be negative. So positive and negative, of course, there is a subtraction. So in case of when the flux is growing, these magnetic fields within the loop are in the opposite direction. And again, only within the loop. What happens outside of the loop, we don't care. Because we just want to suppress the flux. We work with the flux. Flux is within the loop. What is outside? That's outside, right? So now, once we found a direction of the induced magnetic field, external field no longer needed, right? So we can trash it. So now we just need an induced magnetic field, so which is into the loop, right? So now we need to apply right-hand rule number 2, right? Right-hand rule number 2, which we use to find a direction of the magnetic field lines over straight wire, right? So we're going to apply it here. But now we are going to apply it in the reverse direction. Because back then we applied what? We knew direction of the current, right? And then our fingers gave us direction of the magnetic field. Now we have reverse situation. We have information about the direction of the magnetic field, and we want to get information about the direction of the current. So you see a reverse situation. So now, but basically our rule is still the same. So we need to match with our fingers, curled fingers. We need to match this direction within the loop, you see? So I have to position my fingers like this in order to match this direction. Look, if I position like this, directions are opposite. Marker is into the loop, my fingers is out. So this is wrong definitely. So I have to position like this. So that is the correct. And my thumb gives me the correct direction of the induced current. In this case, if I look from this point, it's a clockwise direction. So that's how we find direction of the induced current. Of course, at this point, you can legitimately start screaming at me, right? How come? You apply right-hand rule, which we applied for straight wire, but now you apply it for the loop. All right, so let me justify it. Okay, so yeah, we applied it for a straight wire. All right, let's say current that way. And we applied it to find the direction of the magnetic field lines. And of course, we remember that magnetic field lines form pure circles centered on the wire, right? So we outstretch our thumb in the direction of the current, and curled fingers gives us direction. Fingers give us direction of the magnetic field, right? But what if I now apply the same rule, but not for a straight wire, but slightly bent, just barely bent? What will be different now? The only one thing will be different. So our magnetic field lines are no longer pure circles. They will be slightly distorted circles. But what about direction of those magnetic field lines? I can still apply the same right-hand rule to find the direction. But of course, magnetic field lines are going to be slightly distorted circles. But who cares? In our case, we just want to find the direction. So now, what if I bend my ruler, my current more, for example, to this level? Okay, magnetic field lines, again, will be more distorted, right? They will resemble less circles, right? But what about direction? Still the same. I can still apply the same right-hand rule to find direction of the magnetic field lines, direction of the magnetic field for even bent wire. And if I keep bending my ruler, okay, I like this rule, I don't want to break it. Of course, sooner or later, I will end up with a circle, right? And okay, now of course, magnetic field lines are going to be really distorted circles, right? They wouldn't be even resemble circles, right? But still, direction can be found using the same right-hand rule, right? So I can still apply the same right-hand rule, right, in order to find either direction of the magnetic field lines or direction of the current. So that's why I can still use the same right-hand rule number 2 to find direction of the induced current in this case. Right? Okay, so that was the first situation when flux was increasing, right? Flux was increasing, so the system, the loop rebelled, right? And we discussed the steps, how we can find direction of the induced current. Now, the second situation. What if flux is dying? All right, so again, initial situation exactly the same. So we have some conducting loop. So we have some external magnetic field. Of course, there will be some initial magnetic flux, right, produced by this external magnetic field. And now the second situation, right? So what if that flux is dying in time, right? Again, the first situation, flux was growing. Now it's dying. Okay, so the loop, you remember, it doesn't like when flux changes. Of course, it will wake up immediately and start doing something. Right? So what will be the response of the loop? It will start driving a current, again, electrocuting itself, right? It will start driving a current, induced current, in such a direction So that, again, we don't know right now that direction, but we know God programmed everything properly, right? So it will start driving current in such a direction so that the induced secondary magnetic field is in the same direction. You see cups are in the same direction. So that the secondary magnetic field, induced magnetic field, okay, I feel like I need more hands or more fingers. Right. So the induced magnetic field will be in the same direction as the external magnetic field. Again, within the loop, because what loop is trying to do is trying to now support dying flux. Flux is within the loop. So within the loop, these two magnetic fields, external and induced, are in the same direction. So now, once we know direction of the induced magnetic field, we can trash the external one. We don't need it anymore. Right. So, and now right-hand rule number 2, exactly the same which we just discussed, right? So now we, and again, in the reverse direction, applied in the reverse direction, because we know information about the induced field and we want to get information about current. So now, again, you need to match with your fingers, with your curled fingers, this direction within the loop. So it means that I have to position my fingers like this, right? So in this case, my fingers are out of the loop and marker is also out of the loop, right? Because again, if I position like this, directions are obviously opposite, right? But in this way, directions within the loop are the same. And you see, my thumb, outstretched thumb, gives me the correct direction of the induced current. That's a second part of the Faraday's law. Lens rule. The Lens rule. Second part of the Lens rule. In the case when magnetic flux through the loop is dying. So in this case, system becomes supportive and behaves like a Florence Nightingale. In the first case, it rebels and behaved like a Che Guevara. Right. Okay, so now, after introducing this rule, I like this rule. It's kind of very fancy, but at the same time elegant. Now let's look at the examples, and we're going to practice plenty of examples, so you should be comfortable, right? Okay, so let's imagine this situation. So we have a conducting loop, right? You see, and what if I grab a permanent magnet, right, and move it towards the loop, right? Slowly move towards the loop. Okay, so pretty much up to this point. And I want to know what happens in the loop. Are we going to induce any current, and what will be a direction of that induced current? So here's my permanent magnet, and that's the direction of motion. And let me draw. Every time, of course, we need to know direction of the external magnetic field. Without that, we cannot create this. We cannot start any discussion, right? So, of course, you remember magnetic field lines, they sort of start on the North Pole and end at the South Pole. But, of course, you remember all the time the magnetic field lines form a closed loop. And I was lazy to draw bent magnetic field lines, so I drew them as straight lines, right? It is not going to change the story, right? But anyway, so this is our external magnetic field, right? All right, and so first of all, in order to start applying Lens rule, we need to figure out what? We need to get information about magnetic flux. What magnetic flux does in time? Is it growing or is it dying? And only then we can start applying Lens rule, right? So in order to analyze magnetic flux, again, you remember 3 parameters, B, A, and the angle between them. So we're going to analyze all these 3 parameters all the time. So what can we say, for example, about the area of the loop? It stays constant. We do not distort the shape of the loop changing its area. No, loop stays the same. So area stays the same. Then angle. Okay, yes, strictly speaking, angle will be changing slightly, right? But let's assume that angle stays the same, right? So let's just emphasize, look at one parameter at a time. So let's assume that angle stays the same, right? But what can we but what can you say about the external magnetic field? It definitely changes, and these changes will be the strongest, right? We move closer, we move this permanent magnet closer and closer to the loop. Of course, magnetic field becomes stronger and stronger and stronger. So definitely external magnetic field is growing, and I usually draw something like this arrow at the angle showing that this quantity is growing in time, right? So then area stays the same, angle stays the same, magnetic field is increasing. So what can we say about the flux? Of course, magnetic flux is growing as well. Flux produced by the external magnetic field. So flux is growing. So now at this point, we're ready to start applying Lenz's rule, because now we know what happens with the flux. So we can immediately tell that what will be the response of the system? Yeah, it will definitely start electrocuting itself, right? But in terms of in terms of its response, of course, it will try to suppress this growing flux, right? You remember. So in this case, the system will rebel, right? So, and you remember it rebels in which way? It starts driving current in such a direction so that the induced magnetic field is in the opposite direction to the direction of the external magnetic field within the loop. So over here I can, of course, the picture, right? So this a picture of Che Guevara, right? And of course, the currents, the directions are going to be opposite. You see, B induced, for example, up, B external is down, right? Okay, so now I know the direction of the induced magnetic field. Again, within the loop, because we're trying to suppress the flux. Flux is within the loop. So I can draw, for example, this induced magnetic field lines. I drew it as a circle, right? But of course, you understand, these circles will be really distorted. It just, I didn't want to draw complicated. But anyway, it will be something like this, right? So induced magnetic field. And we're just interested in the direction of the induced magnetic field within the loop. You see, induced magnetic field is down, external magnetic field is up. So within the loop, directions are opposite. That's what we have here, right? So, and that's what I drew approximately, right? Resembling this. Okay, so now we know direction of the induced magnetic field within the loop. And so what's the next step? The last step, right-hand rule number 2, right? This one. So now where is my loop? Okay, here's my loop. And my induced magnetic field, you see that? Okay, I used red. Okay, let me use red. So induced magnetic field is in the loop, is in the loop. Right. So I need to position my fingers like this in order to match that direction. Right, you see? My fingers are down, marker is also down. Right? So, and as a result, my thumb, you see, outstretched thumb, gives me direction of the magnetic field, direction of the induced current. Direction of the induced current. So if I look from the top, all right, so from the top, so current is clockwise direction, if you look from the top. So let me open it up. So yeah, this is the correct direction of the induced current. So in this case, current will flow in a clockwise direction. And so let me complete this line. So I induced as a result has CW direction. So in my case, right, I developed for myself, right, this train of thoughts. And usually I try to write it carefully every step, because it's so easy to make a mistake. At some point, at one point, you are not very attentive. You change the direction. Okay, made a mistake in the direction, and then the rest will be wrong. Of course, if you made 2 mistakes, right, one after another, right, of course, 2 mistakes will lead you to the correct answer. So either make no mistakes or make 2 mistakes, right? In that case, you will end up with the correct answer. But of course, I will be able to spot that you made 2 mistakes, right? Because I usually read your solutions. Right. So, but again, anyway, so I like this train of thoughts, and I usually try to draw it carefully. I write it carefully to avoid any silly mistakes, because it's very simple to make some unnecessary silly mistakes at this point. And I see it every semester. Students even students who know how to apply it, if they are sort of not very attentive, not very careful, they can easily make a mistake, like a silly mistake. Okay, so that is just a blah, 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 which I just told you. Now, next example. Okay, yeah, of course, it must be framed, right, to make it look nicer. All right, so next example. What if we have this situation? We have infinitely long straight wire with a current. And what happens to that current in time, you see, it's decreasing. I don't know, 5 amps, 4 amps, 3 amps, so it's going down in time, right? And let's just bring a loop, circular loop in this game, conducting loop, right, made of metal. So here's this loop, right? And so the question is, can we find a direction of the induced current, if there will be any induced current, right? Okay, so let's start analyzing. Direct application of the Faraday's law. This process cannot be described by anything but Faraday's law. And that's why it is one of the equations from the set of Maxwell's equations, which form foundation of electromagnetism. But anyway, so first step. What's new relative to the previous example? So now, basically, magnetic field lines, external magnetic field, is not given right away, right? We need to first get information about the external magnetic field, which basically creates all this mass. That's what triggers all this, the whole process. And of course, which object creates an external magnetic field? Of course, our current, our wire with the current, right? And so first, in order to find direction of that external magnetic field, again, we need to use the right-hand rule number 2, but of course, in the regular, straightforward direction, right? So outstretch your thumb in the direction of the current, right? And your curled fingers are going to give you direction of the external magnetic field. External relative to the loop, right? That's our object, loop, right? So, and the rest are the external objects, right? So magnetic field produced by an external object. So above, we're going to have dots, right? Yeah. Below the wire, we're going to have crosses. Above dots means a magnetic field is out of the board, out of the screen, and below crosses, it means into the screen. You remember that notation. So now we have information about the external magnetic field. Great. So now, next goal, we need to figure out what happens to the magnetic flux produced by this external magnetic field. Once we know that information about the external, information about the flux, we can start applying Lenz's rule, right? So again, in order to analyze flux, we need to analyze 3 parameters again, B, A, theta, right? Okay, what happens to, for example, angle? Let me start with the angle. Angle, it's, of course, angle will be constant, but of course, angle can be either 0 degrees or 180 degrees. If you pick, for example, area vector into the screen, you remember you have a freedom. If whenever you have a open surface like this, right? You have a freedom. You can position your area vector either this way or that way, no restrictions. I remember the very beginning, mastering physics tried to impose some restrictions. I remember I wrote them a letter. They changed, right? So they stopped doing this. You have freedom to choose, in this case, area vector. So if you pick area vector into the board, the angle will be 0 degrees. But anyway, it will be constant. So it is not going to change magnetic flux. If you pick area vector out of the board, out of the screen, the angle will be 180 degrees, pi, but anyway, it's constant. So in both cases, of course, angle stays constant without changing magnetic flux. Great, so angle doesn't create any troubles. Then area of the loop. Again, we don't do anything with the loop. Right, physically, we don't distort its shape in order to change the area. So area also stays the same. So theta, A are constant. What about magnetic field? But magnetic field is changing because current, the current in the wire is decreasing. So of course, magnetic field, external magnetic field is also decreasing. So now I can write, so B external is going down. As a result, magnetic flux produced by this external magnetic field is also going down. right? So now I can draw this. So you see, previous example, in the previous example, magnetic flux was growing. So the response of the system rebelled, and now you see flux is dying. So I'm trying to discuss both of these situations, right? So now flux is dying. Of course, the loop is not going to like it. Damn it, again, you're trying to change the flux through me, right? So loop doesn't like it, and of course it responds. In which way? It becomes supportive. It see this dying flux, right? It will try to support it like Florence Nightingale. And again, you need to realize it is not going to support it forever. It doesn't have enough energy, right? So it will support for some short period of time, right? Anyway, the flux will die, right? If it was dying. That's what I was joking, right? Like Florence Nightingale, or you poor soldier, right? You you're suffering, let me help you. You will suffer longer, right? So anyway, so the flux will do, but will go down, but it will go down slower, right? And so now let's see the response of the loop. Of course, it will start driving the current in such a direction so that that induced magnetic field will be in the same direction as the external magnetic field. Again, so in order to support dying flux. So now I can draw something like this, of course, picture of the Florence Nightingale, okay, cartoon, right? Right. Another picture, but you see now these two magnetic fields are in the same, directions are the same. Because now both fluxes must be, for example, positive, so that dying flux will be supported by flux produced by the induced magnetic field, right? Okay, so now after this, once you know direction of the induced magnetic field, now the last step, right-hand rule, in order to find the direction of the induced current, right? So again, where's my, so this is my, yeah, I forgot to say, of course, now once we know the direction of the induced magnetic field, I usually draw it on the picture. You see this red crosses, that those red crosses represent our induced magnetic field. And you see the directions the same. So crosses represent external magnetic field, crosses represent induced magnetic field, right? And so now, so crosses, it means that magnetic field is into the screen. So it means that it's something like this, right? Into the screen. Right, so in order to match that direction, in order to match, so this situation, right? In order to match this direction with my finger, this direction with my fingers, or I have to position my fingers like this, bent like this, right? No, it's better like that, right? No, like this, right? And so you see my outstretched thumb gives me correct direction of the induced current. So it will be clockwise. I'm getting clockwise direction, right? Yeah, clockwise direction. Okay, so now conclusion final. So induced current, direction of the induced current is CW, clockwise direction. Right? So you got the idea, right? And again, you can, if you don't like this train of thoughts, you can try to come up with your own, but everything must be explained, right? So if you just, for example, on the exam or on the test, just write down the correct answer, I can accept it only if it's a multiple choice question, maybe right. But in the problem, I want to see your analysis. I want to see your speculations. Plus, every time, chances of guessing it very high, 50%. It's either clockwise or counterclockwise, right? All right, okay, so again, let's frame it to make it look nice. And now, question for you. Now, after these two examples, you should be able to apply that by yourself. So we have this situation. We have, again, current, okay, wire with the current. And what happens to the current in that wire? It's increasing, again, in time, increasing in time. Right? And there's a loop. Now it's a sort of rectangular loop, not a circular loop, but what's the difference? Current doesn't care if you have rectangular loop or triangular loop or circular loop or distorted circular loop. It will still drive the current in the clockwise or counterclockwise direction, right? So that shape of the loop shouldn't scare you, right? And so which is correct? Which statement is correct? So in this case, induced current will have clockwise direction, counterclockwise, and no induced current in the loop. So give it a try. Now let me continue. So I will analyze in exactly the same way like I've just discussed with you. First of all, we need to see the direction of the external magnetic field, which creates all this mass. And again, so first, right-hand rule number 2. On this side of the wire, magnetic field will be out, but in the loop, it will be into the board, right? Oh, I need to bring my slides forward. That's why I cannot flip. All right, so it will be something like this. Yeah, into the loop crosses, into the screen we have crosses, and on this side we have dots, right? So right-hand rule number 2. Now, so this is information about external magnetic field, B external, you see. So now we need to analyze what happens to the magnetic flux produced by this external magnetic field. Again, 3 parameters, BA theta. Area of the loop stays the same. We don't change the area. Then angle. Area stays the same. Angle, again, you can make it 0, you can make 180 degrees. It's up to you. But in both cases, area, the angle is going to be constant, right? So it's not going to change our the value of our flux, magnetic flux. So area constant, angle constant, but magnetic field, external magnetic field, of course, it is increasing because the current through the loop, through the wire, through this wire with the current, since this current is increasing, of course, external magnetic field is increasing as well. So since B increasing, so it means the flux produced by this external magnetic field is also increasing in time. So I can write phi sub B, and it's going up, again increasing in time. So now once we get to this point, now we can start applying a Lenz's rule. So now we can tell immediately what will be the response of the system. Again, it will try to electrocute itself, right? It will start driving current, and of course in such a direction so that the induced magnetic field, so it rebels. So the induced magnetic field will be in the opposite direction to the direction of the external magnetic field, right? Trying to suppress the flux. One flux will be positive, the other flux will be negative. So there will be suppression. So directions of these magnetic fields are going to be opposite. So in this case, the system rebels, behaves like Che Guevara, right? So now, once we know the direction of the induced magnetic field, now first of all, every time I usually draw dots or crosses representing that induced magnetic field. So since direction is opposite, external magnetic field are represented by the crosses. So it means that induced magnetic field must be represented by the dots. Within the loop, what is outside of the loop? Who cares? The system is trying to suppress the flux in this case. So within the loop, I can draw a bunch of dots. Those dots represent induced magnetic field. Okay, so now once we got to this point, now right-hand rule number 2, but of course applied in a reverse direction. So this is my loop. Induced magnetic field dots, it means out, right? So magnetic field is out, induced magnetic field. So it means that I have to position my fingers like this. Right. Okay, like this, right? To match that direction. And my thumb gives me direction of the induced current, right? Yeah, dots out. Yeah, so this is the correct situation. So induced current is going to flow it's a counterclockwise direction. Counterclockwise direction. All right, so yeah, counterclockwise direction. Good. So it means that the correct answer is B. So what did you give me? Yeah, most of you answered, picked B. Great. Right. So that's how I would analyze it. So now the next question. Yeah, so B is the correct answer. Next one. Question 5, and again, it is in the chat again, number 5. So what do we have here? Again, infinitely long straight wire with a current, but now current stays constant. So current doesn't change in time. And magnetic field lines, external magnetic field lines are given. You see on that side, of course, crosses, it means into the screen, dots out of the screen. Then there is a conducting loop. And now we just, before all the time, our conducting loops stayed at a certain place, right? We did not move them. But now let's grab this conducting loop and let's start dragging it straight down. So parallel to the direction of this wire, right? So along this wire. So what happens, what can you say about the induced current in the loop as you drag this loop down? So direction of the induced current clockwise, counterclockwise, no induced current. Give it a try, right? And then I will discuss. Again, we need to find out what happens to the magnetic flux, right? Direction of the external magnetic field is given, so we don't have to do that. So what happens to the flux? What happens to the flux? Magnetic field, external magnetic field. What happens to the external magnetic field through this loop? In time, nothing. Current stays the same, right? So magnetic, of course, you guys, you need to understand this. Of course, magnetic field changes in space, because as you move farther and farther away from the wire, of course, the value of the magnetic field gets smaller and smaller and smaller. But those changes are in space with the distance from the wire. But we are interested what happens to the magnetic field in time, because you remember in the Faraday's law what we have: d phi over dt, rate of change in time of the magnetic flux, right? So magnetic field changes in space, but we don't care about that changes or those changes. We only want to know what happens to the magnetic field in time. And in this case, since we drag this loop along the wire, magnetic field as we drag stays the same in time. It doesn't change, right? So magnetic field in this case stays constant. Then area, obviously constant. We do not distort the shape of the loop, right? And then what about the angle? Again, constant. Of course, you can make it 0 if you align your area vector into the board, or 180 degrees if it's out of the board, but in both cases, angle will be constant. So all of these three parameters, B, A, theta constant, so flux is not changing. So this loop will be completely happy. It is not going to do anything, it will continue sleeping, right? It will not respond with anything. So in this case, there is no any current in this loop, in this case. I'm trying to flip, but slides are not in front. All right, so here. So that's my blah, blah, blah. Right, agree. Right. Now sort of like follow-up question. Yeah. How should we move? How should we drag our loop in order to actually get a non-zero induced current? Of course, if you, for example, change the direction of this drag, if we drag this loop straight up, again, along the wire, again, the response will be the same, right? So the loop will be sleeping, right? So because flux is going to be constant, so the loop is not going to respond, producing induced magnetic field, right? But what if I, what if I grab this loop, right, and start moving it, for example, farther away from the wire? What will happen in this case? Now, what happens to the magnetic field as we move the loop that way? So magnetic field becomes weaker and weaker and weaker, right? Because you remember, magnetic field changes in space. But now, since we move the loop, right? So magnetic field through the loop will be changing in time, right? Because position of the loop we're changing position of the loop. So now as we move loop farther and farther away, so magnetic field gets weaker again through the loop. Magnetic field through the loop is getting weaker and weaker as we move, right? So areas of the loop still the same. Angle still the same, 0, 180 degrees, it doesn't matter. In both cases, it's constant. But magnetic field now changing in time. So as a result, the loop, of course, will wake up. Damn it, again, you're trying to change magnetic flux through me. And it will start driving current in a certain direction. And let's assume, for example, clockwise direction. I'm just making up, maybe making it up, right? I don't want to analyze it one more time. So let's assume that if I move that loop that way, let's say clockwise direction. But then what if I start moving loop, for example, closer to the wire? Again, magnetic field changes in time, but now magnetic field increases. And of course, the response of the loop will be different. So let's say, of course, opposite, counterclockwise, right? So now if I stand here and move this loop like this way, this way, this way, that way. So what I'm going to get? So when I move there, that way, clockwise. Opposite direction, counterclockwise, clockwise, counterclockwise, CW, CCW, CW, CCW, right? What I'm doing? I'm working basically like a current generator, AC current generator, right? So current clockwise, counterclockwise, clockwise, counterclockwise. I'm sort of like a generator, converting my mechanical energy or energy of my breakfast into, no, dinner. I didn't have a breakfast, right? Converting energy of my dinner into the energy of, into the electric energy, right? And of course, I will be, in this case, expensive generator, right? So, you see, if we move loop in this direction, right, perpendicular to the wire, of course, in this case, current will be produced. But if you move the loop along the wire, nothing.